You probably remember from calculus and even earlier that a function of a function of a variable is a new function of a variable. Well, linear transformations are functions too. So a linear transformation of a linear transformation is a new linear transformation. That's called the composition of linear transformations. So the idea is that if u, v, and w are vector spaces, and let's say that T1 is a linear transformation from u to v, and T2 is a linear transformation from t to w, and we can combine them to make a new linear transformation. T2, T1 from u to w is also a linear transformation. Alright, now why did I write T2, T1 instead of T1, T2? Well, when we compose functions, we work from the inside out. So note that if we have some vector little u in the vector space big U, then T2, T1 of u, which is T2 of T1 of u, is, well, T1 of u is going to be something in V. So T2 of something in V T2 of something in V ends up in W. So even though we're going from U to V to W by T1 and T2, we're really starting with something in U, applying T1 to it, and then applying T2 to it. So it gets written backwards from the diagram. So now if we choose bases for the vector spaces, then these linear transformations turn into matrices. So if we choose bases for U, V, and W, so that matrix of T1 equals A1 and the matrix of T2 equals A2 with respect to the bases that we've chosen, so the matrix of T2, T1 is just A2, A1. So the easiest possible thing. Let's do an example of this. Let's let V of sub k be polynomials of degree less than or equal to k. And let's define T1 from V3 to V2 by P of x gets mapped to derivative of P of x. And let's define T2 from V2 to V3 by P of x gets mapped to x times P of x. And let's find the matrices of T1, T2, and T2, T1. Now they happen to both be defined here, because we could start in V3, get mapped to V2, and then get mapped to V3, or we could start in V2, get mapped to V3, and then get mapped back to V2. So let's find the matrices of both of those linear transformations with respect to the natural bases of the two spaces. And the natural bases are 1x x squared and 1x x squared x cubed. So we really just need to find the matrix of T1 with respect to the bases, the matrix of T2 with respect to the bases, and then multiply. So let's look at the matrix of T1. T1 maps 1 to 0, x to 1, x squared to 2x, and x cubed to 3x squared, because T1 is differentiation. Now 0 has coordinate vector 0, 0, 0, 0, because it's 0 plus 0x plus 0x squared plus, we're going to V2, so that's all I need. 0 plus 0x plus 0x squared. And 1 is 1 plus 0x plus 0x squared. 2x is 0 plus 2x plus 0x squared, and 3x squared is 0 plus 0x plus 3x squared. So the matrix of T1 is first coordinate vector, second coordinate vector, third coordinate vector, fourth coordinate vector. Matrix of T2 so T2 is going to go from V2 to V3. So we're mapping 1 to x when we multiply by x. We're mapping x to x squared and x squared to x cubed. Now the coordinate vectors are the coordinate vectors of these results in the basis for V3. So x is 0 plus 1x plus 0x squared plus 0x cubed. X squared is 0 plus 0x plus 1x squared plus 0x cubed. And x cubed is 0 plus 0x plus 0x squared plus 1x cubed. So the matrix is first coordinate vector 0, 1, 0, 0, second coordinate vector 0, 0, 1, 0, third coordinate vector 0, 0, 0, 1. Let me just note what these linear transformations are. T1 from P3 to P2 sends P of x to its derivative. T2 from P2 to P3 sends P of x to x times P of x. So if we apply T1 first and then T2 later, so take a derivative and multiply by x, then we're going from P3 back to P3. So this one has matrix. We'll put the matrix of T1 on the right, the matrix of T2 on the left. So 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1 times 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, and we get 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 2, 0, and 0, 0, 0, 3. Then T1, T2 is a map from P2 to P2, because T2 starts in P2, gives us something in P3, and then T1 gives us something in P2 again. So we end up back in P2. Now this has matrix. We multiply the matrices in the opposite order. 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3 times 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. And we get 1, 0, 0, 0, 2, 0, 0, 0, 3. It's actually almost the same, but that's an accident. That's not always going to happen. That if the two linear transformations are defined in either order, the matrices aren't necessarily going to come out looking similar. But they did in this case. And let's just see that they make sense. So let's look at T2, T1, A0 plus A1x plus A2x squared plus A3x cubed. T1 takes the derivative. So we've got T2 of A1 plus A2x, oops, 2A2x. Plus 3A3 x squared. And then T2 multiplies that by x, so we've got A1x plus 2A2x squared plus 3A3x cubed. And if we take the matrix of T2, T1, that's 4 zeros, 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, and multiply that by A0, A1, A2, A3, the coordinate vector of this polynomial with respect to the natural basis, we get 0, A1, two A2, and 3A3. And that happens to be precisely the coordinate vector of this polynomial with respect to the natural basis. So they match, which is good. Now let's do the other direction. If we apply T1 to T2 to a polynomial, T2 applies to polynomials in P2, so those are polynomials of degree at most 2. So we multiply by x, and we get A0x plus A1x squared plus A2x cubed. And then T1 takes the derivative of that, so we got A0 plus 2a1 plus 3a2. And if we multiply the matrix of this linear transformation by that coordinate vector, we've got 1, 0, 0, 0, 2, 0, 0, 0, 3 times a0, a1, a2 is the coordinate vector here. We've got a0, two a1, 3a2, which is exactly the coordinate vector. Oops, I forgot my x's here. T1 takes a derivative. So there's no x there, but there is an x here, and there's an x squared there. But anyway, so the coordinate vector of this polynomial is a0, 2a1, 3a2, which is precisely what we got here. So those match as well, which is good. The end.